All right, let's take a look at our first real method for solving differential equations. So this is kind of the method we learned in Calc 1, even though we didn't call it like that. So it's called separable equations, or equations that are able to be separated into their individual variables on each side. So by looking at this, let's take a look at something we might have seen in Calc 1. I think we showed in a previous lecture something like y prime equals 2x, and I said solve for y. Well, to do this, as far as we're talking about today, separable variables, you always want to write your derivative in differential form. Now, the idea for this is we should be able to get everything that has an x on one side and everything that has a y on the other side. And you see, we could rewrite this kind of in differential form, if you want to think about it like this, as 2x dx. All right, now that we've isolated all the x stuff on one side and all the y stuff on the other side, all we have to do is integrate. So we integrate dy, integrate 2x dx. Of course, on this side, the integral of dy is just y, and the integral of 2x is x squared, and plus our integration constant. So that's the entire idea right there behind separable equations. If you were able to get all the x stuff on one side and all the y stuff on the other side, or whatever letters you're using, then all you have to do is integrate both sides to finish solving. So let's just take a look at a few examples here. What if I said dy dx is equal to xy over x plus 3? Now, the way you want to look at this, if you want to try to separate an equation, is we just got to try it. You can say, can I do this? And you might have to do a whole bunch of algebra to get there. But let the differential lead your way. So if you notice, if I clear this differential, and we end up with this xy over x plus 3 dx, this is already kind of telling what you need. You need any functions of y on the left and any functions of x on the right. So you can see I could get all the y's on one side if I just divide both sides by y. So 1 over y dy is equal to x over x plus 3 dx. So now to finish this, since I have all the x stuff on one side and all the y stuff on the other side, all I have to do is integrate. Well, I say all you have to do, like that's the easy stuff, but this is actually where it gets difficult, because you have to go back to all those old integration techniques that we learned in the past. Now, of course, the integral of 1 over y is the natural log of the absolute value of y. How do we integrate this side over here? Well, anytime you have a rational expression and the degree of the top is greater than or equal to the degree of the bottom, you need to do long division first. So we need to do x plus 3 into x. Okay, so what do? And of course, that's plus nothing. What do I have to multiply x by to be x? That would be 1, distribute, and then subtract. So we get negative 3. So that's our remainder. So that's going to be plus negative 3 over x plus 3. Okay, so which means we can break this into two integrals that we should be able to handle. This will be the integral of 1, 3 over x plus 3 dx. All right, let's go ahead and bring this up over here. Hopefully there's just some scribble work. It's gone. So we get the natural log of the absolute value of y is equal to the integral of 1 dx minus 3 times the integral of 1 over x plus 3 dx. All right, again, both of those integrals now should be pretty easy for you to do. That's just x minus. Now, to actually do this integral here, I'm going to kind of skip some steps because hopefully we're getting better at integration by now. Here you would just do a regular u du substitution. You let u be the denominator. The derivative of that would just be dx. So this is really just 1 over u du, or natural log of absolute value of x plus 3, plus some integration constant. All right, now here's where it gets a little messy. What I mean by a little messy is we're told to find the function y. Now, if it's easy to solve for y, you're generally going to want to try to do that. But a lot of times we leave our answer here implicitly like that it is. Like I said, if it's really easy to solve for y, go ahead and solve for y. But if you end up with something really messy in the end, you may not want to do that. All right, let's take a look at let's do one more example. Let's see here. It's just the integration part that's going to be your struggle with these types of problems. So let's say if we had, let's make this one easier. Let's say dy dx is equal to, I don't know, x plus 5 over y. All right, separation of variables are generally your first thing you want to try when you're solving a differential equation because it's going to be our easiest method. The idea is, can we get all of our x stuff on one side and all of our y stuff on the other? Again, we're going to let our derivative lead the way. When I separate my derivative, I see I want the x stuff on the right and the y stuff on the left, which of course that's easy to do in this one. X plus 5 dx. Now I'm getting a little sloppy here. Technically there should be parentheses around that, but kind of like that. But most of the time with our derivatives that we've done in the past, we've been pretty sloppy with them and just kind of left them out at the end, which I'm still okay with that. All right, now that we got all y stuff on one side, x stuff on the other side, go ahead and integrate. So we have y dy is equal to the integral of x plus 5 dx. Of course, this is going to be 1/2 y squared is equal to 1/2 x squared plus 5x plus some integration constant. Now, as soon as you've integrated both sides, now is generally the best time to apply any initial condition. So let's go back up here and say that this problem gave us some initial condition. Let's say we know something like y of 0 is, actually let me change that, we already got 5 in there. Y of 0 is equal to 2. So this should help us figure out what our arbitrary constant is here. So if we plug that in, so y of 0 is 2. So if x is 0, y is 2. So that's going to be 1/2 2 squared, 1/2 0 squared plus 5 times 0 plus c. So that's going to be 2 is equal to c. So now our solution so far, we got 1/2 y squared, 1/2 x squared plus 5x plus 2. Now again, you may or may not want to solve for y here. This one would be fairly easy to do. Let's multiply everything by 2. So that's going to be x squared plus 10x plus 4. Then take the square root of both sides. Of course, you do get a plus or minus here. So we get x squared plus 10x plus 4. All right, so generally as soon as you integrate, applying the initial condition right then is most of the time the easiest place to do it if you do have an initial condition. All right, let's take a look at, let's do one more here. Let's say I have y prime is equal to y over x. All right, looks easy, and overall it's not going to be too bad. Let's see what happens here. Again, here we get dy dx is equal to y over x. All right, if we're going to separate our variables, we do generally let the derivatives lead the way. So we get dy is equal to y over x dx, which means I want the y's on the left and the x's on the right. So to do that, I'm going to get 1 over y dy is equal to 1 over x dx. All right, so if we integrate both sides now, pretty easy integrals to do, 1 over y dy, integral 1 over x dx, we end up with the natural log absolute value of y, natural log absolute value of x plus c. Now here's the reason for doing this problem. This would actually be fairly easy to solve for y, but we can actually make this a lot easier than what it is. Remember, c is an arbitrary constant. It's any number that you want it to be. Now, if you have logarithms in here, it might be helpful, watch, instead of saying that c, let's call it the natural log of c. Because if c is an arbitrary number, the natural log of c is still an arbitrary number. But by doing that, I'm actually able to simplify the right-hand side a little bit. So I get the natural log of the absolute value of y is equal to, here if you're adding logarithms, that means you can multiply the arguments. This would be the natural log of c times the absolute value of x. Now you can exponentiate both sides. So you get e times the natural log absolute value of y, e natural log c absolute value of x, or the absolute value of y is equal to some constant times the absolute value of x. You could leave it like that. Depending on how the book goes here, this can be a little tricky. The absolute value gives you a plus or minus, something like this. However, some textbooks, since that's an arbitrary constant, and they may actually absorb the plus or minus into the c there. All right, so you see you got a lot of different options when you have your arbitrary constant. Sometimes it's helpful to represent that arbitrary constant other than just a letter. And you can do any trick like this as long as it stays arbitrary. If you notice that there's a big difference between your answer and the back of the book, look to see if they played with that constant. That may actually be how they got to their answer compared to yours. All right, so get all your x stuff on one side, all your y stuff on the other side, integrate, and if it's easy enough, solve for your dependent variable.